Of course, our last talk today to Freitag, Berkeley, Jouanolou type theorem. Oh, my apologies.
It's okay.
From UCLA.
All right. Thanks very much for the invitation. This is a joint work with Rahim. It's been mentioned before already. We started it during MSRI, and then for a long time we were stuck, and then now we've gotten a little farther, I guess. So here's the first way to describe what we're interested in. So we have a system of ordinary differential equations. So some number of equations and some number of variables. It doesn't matter how many either are. And it could be the case that from the solution set to our system of differential equations, we have a differential rational map, which I call phi, which takes our solutions to the field of constants. So there's just one variable here. So it's to the field of constants of whatever field we're working in. That could happen, or it might not. Of course, whenever I write something like this, I mean that phi is a non-constant map. So it's a non-constant map to the constants. If that does happen, then it's not hard to see that if you look at the inverse image of any particular point over here, you look at the set of points here which map to it, that this is what we call a co-order 1 differential subvariety. And in the language that's been used in this workshop so far, this means that the subvariety has Colchin polynomial, which is given by the Colchin polynomial of the original system minus 1. So it's the analog of codimension 1, if you like, but for the Colchin polynomial. So, all right. And in the talk, we're going to explain why, well, at least in certain situations, the converse is true. The first situation is the simplest one, when we start with the differential field consisting of all constants. We'll move on to explain some circumstances in which we can say this is true. It's not always the case that this has to happen.
And what's the point of considering this?
Well, so this is, we'll get to some applications, of course, later in the talk. But this is one very particular way in which you can have an infinite collection of co-order 1 subvarieties. And what we're going to explain is that this is the only way in which you can. So if you had a map like this, you would get a collection of an infinite collection of co-order 1 subvarieties. But what we'll explain is that if you have an infinite collection of co-order 1 subvarieties, then you can get a map like this. So
is it related in any way to expressing solutions with tried by constants, or what is it?
yeah, that's one thing that it's related to. Yeah, we'll get to some issues around that. I think it will become clear. I'll try to explain this from a couple of different perspectives and give some sense of the applications. Okay, so most likely we're going to focus on the case where you might want to think about the case where the system has finite rank. And if you remember Dave Marker's talk from yesterday, what that means is that the transcendence degree of the differential function field of the variety is finite. And for yeah, Alice?
So you're talking about derivation?
Yeah, derivations.
One derivation.
Yeah, one derivation. Yeah, for right now. Maybe we'll talk about more in a little bit. Okay. So we could state this special case in some equivalent terms, maybe more geometric terms, and I'll try to explain. So this is the D-varieties approach, but I want you to get a picture of the geometry of the situation so that you have some intuition for the problem. So suppose that you're given a variety V and a map from V to the tangent bundle of V, a regular map, just an algebraic map, nothing to do with differential algebra. It's on the board now. So then you call a subvariety S invariant, or in the language from yesterday, a D subvariety of V, if when we restrict the map S to W, we still get a section of the tangent bundle. And so what that means, for instance, if this is a picture of a surface, then to give a section of the tangent bubble on that surface, you're essentially picking a direction at every point. I couldn't draw them all. And to give a variety W, which is S invariant, you have to draw a curve on the surface so that at each point you draw an arrow, the arrow points into the tangent line of the curve at that point. Right?
I hope you didn't use this teaching calculus.
No.
I use this. I hope because the tangent lines.
Will look like the tangent.
All right. So, no, I'm not using this picture anywhere except here. Okay. So this is a description of what's going to happen. Okay. If you have an invariant subvariety, and what we'll prove is that you have infinitely many invariant subvarieties if and only if you have a map from V to affine one space, so that the fibers of that map give you the invariant subvarieties. That's the only way that this can happen, if you have infinite. Okay. So, all right. Now, okay, so I've talked about two perspectives on the problem we're going to think about, but we have to work when we begin, we're going to work in a slightly different setting to prove the initial geometric statements. Eventually, these statements are going to be used to prove statements like the ones I had on the board before. Okay, and I want to explain what exactly you have to do in the case of partial derivatives to prove statements like the ones that I'm talking about, what sort of geometric work you have to do. And then I'll specialize to the ordinary case and give you some ideas about the proof. So I want to take the nth power of the tangent bundle. You can think about it that way. And it's not. I don't want to concentrate on the formalism here, but at any given point A in X, this is just the nth power of the tangent bundle, and then it's glued together in the expected way. Now, I'm not going to be thinking about sections of this bundle or of any bundle in this part of the talk. Instead, I'm going to be thinking about forms or sections of the dual bundle. Okay? So here, I mean, if you want, you can take X to be a projective algebraic variety, or you can take X to be a compact complex manifold.
X is smooth.
If it's a variety, that's not strictly necessary. The result will be true. You'll see why, for the kind of result that I'm proving, the smoothness doesn't matter, because the family of coorder 1 subvarieties will be dense in the whole variety, so you can restrict to an open subset of the smooth ones. So you may as well assume that the variety is smooth, but the results don't depend on it. So, or you can think about it, if you want to think about it as a compact complex manifold, that's fine as well. All right. And so these are the appropriate objects to think about in the partial, for proving the geometric result that we're going to use for partial differential algebraic result. And we're not just going to think about this sheaf of forms. At some point we'll have to think about the p-th wedge product of that sheaf of forms. So locally, so from this point forward in the talk, I just wanted to give you the idea of the objects. You can think that these are the objects that you would use if you want to prove the geometric result that we'll later use for studying systems of partial differential equations with many derivations. But from this point forward in the talk, I'm going to let m be equal to 1. And if that's the case, if you have some local coordinates xi, these are local coordinates on x, then you can think of it locally for some p many local coordinates on x. We can think of the objects in here as being locally given by the wedge product of these forms. Okay. So it may be useful to just think about, special cases. And I think that the proof in the case where m equals 1 versus the proof in the case where m is arbitrary does not involve significantly different ideas, just different objects and slightly different computations. Okay. All right. So now I want to tell you about the setup for how we describe the differential equations in this language with these objects. So I have what I call a codimension P holomorphic foliation on X. And it consists of the following data. We fix some open cover of X first. Then on each piece of the open cover, we have some wedge product of these forms. So alpha 1 through alpha p. It should be, and it's not equal to 0. So what that means is that those alpha 1 through alpha p are linearly independent. Okay? In that vector space. And we also have on the intersections transition maps between the wedge products of one forms. Now, I'm not so interested actually in, I'm not so interested in certain sheaves on certain manifolds. I'm more interested in definable sets because I'm a model theorist. And so I'm not really interested particularly in this sheaf, but rather, or the objects in the sheaf, but rather the information that it encodes. And the information that I'm thinking about encoding here is the common kernel of these differential forms. Remember, each differential form is a linear map from the tangent bundle, let's fix a point. Each of these is a linear map from the tangent space at that point to the field, f(1) space if you like. And if I look at the subset where that form vanishes, I have a linear subspace. And because this is a non-zero wedge product, the codimension of the linear subspace that's the common kernel of each of these forms is codimension P. So that's, I'll say that in a moment. So, maybe I don't say that, but I'm telling you. Okay, so that's really what I'm interested in. And if you want to think about the actual objects, this codimension P holomorphic foliation, then you can, because the transition functions define a line bundle, you can think of this omega, that's our codimension P holomorphic foliation, as being an element, as a global section of this is the p-fold wedge product of those one forms tensored with this line bundle. Okay, so again, for getting the idea of the proof, it's not, like I say, it's not so important to completely understand the objects in here, but rather the information that they encode. Okay, so I do say that. I say that next. So I'm just going to repeat this to emphasize it. At each point, we're really interested in this kernel. So I'd like to draw a picture of maybe the simple case. So if you fix some point on the underlying manifold or variety, let's say that P equals 1 and the dimension of the variety is 2. So it locally looks something like that if you like. Then, well, if I fix this point, the information that I'm giving by some element in omega 1 tensored with L is basically at each point I have giving some line which lies in the two-dimensional plane that is the tangent space at that point. And okay, so you can see it's giving some similar but distinct information. Yeah.
In the definition of a foliation, don't you also need a kind of crossover condition on the Ghys?
Yeah, but they satisfy. Yeah, that's true. You do need that, but they satisfy that by thinking about this, by thinking about that requirement there. Yeah, you can see that now if you apply GJI to GIJ, that you'll have to get back WJ, and then you have a rational function times one of these forms, and you have equality, so you'll know something about that rational function, the identity. All right, now I have to say what I mean by a solution. So a solution, by solution, I'm only going to be looking at hypersurfaces in my original manifold or variety. And so by solution, what I mean is that it's a hypersurface so that at each point, A and Y, I contain the subspace. And recall that this was the subspace which is the common kernel of my forms. So, in other words, the line that the forms cut out in the tangent space of that point should be the tangent line of the curve, if you want a curve to be a solution in that picture. Okay. So, that's somehow the geometric meaning of what's going on. And what does it mean locally in terms of the form algebraically? Well, here's what it means. Y is a hypersurface, and that means that it's given by the vanishing of some function on each open set. And df at the point A vanishes on WA. That's the same thing as insisting that the wedge product of df with the omega is 0. Okay. And, well, there's other equivalent algebraic formulations of what this means. So just to get you used to the idea, here's another one. So generally, f is on each open set, it's a sort of rational function, which is defined on that open set. But I mean, a priori, if you pick an arbitrary f, if you write down this wedge product, you have no reason to believe that this is a holomorphic form. It could be that there's points where this is not defined, where the denominator vanishes. But to say that y is a solution, or this happens, precisely means that this is a holomorphic form. And the way to see that is that the only way for, let me just put the calculation on the board. So if you look at this, the Fi is the generator of this ideal in that field of in the ring of regular functions on UI. And so this being equal to 0 there precisely means that it's some non-zero power of some positive power of Fi times a holomorphic function there. So now this wedge product here has a positive power of Fi times some form. And so when you divide by Fi, you're not left with anything in the denominator. So it's just to explain something about the algebra and how you manipulate these things. Okay. All right. So we'll define a meromorphic first integral for omega to be some f. This is in the function field, but non-constant. Okay. So that this wedge product is 0. And so you can think about, if you think about this, what this means is that f is a map from our variety x to affine 1 space, if you like, or to projective 1 space, if you like. So that when you take this wedge product, you get 0. But now it's not hard to see that the level sets defined by f of x equals a will determine infinitely many solutions in the sense that I hypersurface solutions to omega in the sense that I've defined things. Because if you take the equation f of x equals a and you take d of that, well, that's just d of f because d of a constant is 0. Okay? So what the theorem in this language says is that the only way to have infinitely many solutions is to have a meromorphic first integral. Okay? So hopefully I've explained it from several different perspectives. And I mean, this is an old theorem. I think that the first version of this theorem is due to Jouanolou, or the first one that I know about. Perhaps it goes back much farther. And so Jouanolou looked at the case where m equals 1, p equals 1. There were some more assumptions about omega and x, but you could get rid of those assumptions if you assume that x is a smooth projective variety, for instance. And that's primarily the case we're interested in. Sometime later, Hrushovski, in an unpublished manuscript in the 90s, basically reworked Jouanolou's technique, and his manuscript proves many more things not related to this directly that Jouanolou considered. But working in the case where m equals 1 and p was arbitrary, although of course you can see that p should definitely be between 1 and the dimension of your variety minus 1. But with some similar technical assumptions, I don't think he was really concerned with removing those, because the case, again, the case that Udi was interested in was really the case of smooth projective varieties. So in a paper from around 2000, Ghys looked at the case m equals 1 and p equals 1, but removed all of these technical assumptions. And those, removing the assumptions was not what I think interested us at all, but somehow the proof that Ghys gave is, I think, either conceptually clearer or simpler in some ways, for me and for you. Okay. Is that right? Would you agree? Okay. Okay. So Rahim and I have generalized this, and essentially working in the way that Ghys does to arbitrary m and p. But I don't think that the ideas are too significant. I really don't think that the idea of the proof is any different than just amalgamating cases. But of course, we'll go further. But I think the ideas in the proof are really interesting. So I'd like to talk about the idea of the proof, at least in the special case where m equals 1. Okay. So here's just some notation. By div x, I mean the group of Weil divisors on x. So I just mean formal sums of codimension 1 irreducible subvarieties. And I'm really going to be thinking about, okay, so this is just the abelian group, so Z linear combinations, but I want to tensor with C so that I can think about it as a vector space. Okay, so now I want to define a map, which I'll call the D-log map, from there to the to H1 of X, okay, and the space of 1 forms. Okay, and the way that I want to define this map is the following. It involves the transition functions of the defining equation. So f is defined by the equation fi on the open set ui, and the gij's are the transition functions. And well, what I'm doing is taking the logarithmic derivative in a certain sense of the transition functions on each on pairs of sets in the open cover.
These GIJs are different than your old GIJs.
Oh, sorry. Yeah. Right. Formerly, yeah. Sorry about that. Formerly, there were some GIJs which appeared as transition functions of omega. These GIJs are transition functions for the functions that define my hypersurface. Good point. But they're defined there. Yeah.
Is it obvious that what you just defined at the end of the last slide is well defined?
No, you need to show that. But I don't want to get bogged down in those.
Okay, that's fine, that's fine.
Yeah, all of the things I'm going to define would require you to show that they are well defined, but you have to do some calculations. But it's not too bad to show that. But I think it's non-obvious. All right. So the reason to define this map is really to think about the kernel of this map. It turns out, and it turns out that on the kernel of this map we can define another function whose usefulness I'll explain in a moment. Okay, so how you define this map? How long do I go to? A little after 2. Okay. I think I'd like to skip the part where I define this map. But the point is that this map psi C that I'm defining here, you can't define it on all of the space of divisors tensored with C, but I can define it where this D-log map vanishes. And
So the principle.
so, yeah, so this is explaining why it's well defined. I think I need to skip that in the interest of time. Okay, telling you exactly what it is. Instead, I want to talk about the idea of the proof. So basically, the idea of the proof is that we need to, in order to see that there's only finitely many hypersurface solutions, we need to look at the sub-vector space in div X tensored with C generated by our solutions and show that that's a finite dimensional vector space. Okay? And this is a map of vector spaces, and the one on the right is a finite dimensional C vector space. So in order to prove what I just told you I wanted to prove, I only need to show that the solutions of omega generate a finite dimensional vector space in here, but that means that I only need to show that the solutions of omega intersect the kernel of this map to generate a finite dimensional vector space, since this is a map to a finite dimensional vector space. Okay, so that's what I've just said here, to show that that's finite dimensional. Now, this map C is injective, and even though it's not a map to a finite dimensional C vector space, it would, since it's injective, it's sufficient to show that the image is a finite dimensional C vector space. Okay, so here's a rough picture of what's happened. So we have here the space of all solutions to omega, all the divisors that solve omega. Here's a finite dimensional C vector space. So if we want to show this is finite dimensional, we can restrict to the kernel of this map here. Now, this is not a finite dimensional vector space here over C. This is the space of mirrormorphic one forms. But it is a finite dimensional C of X vector space. And so if the image, sorry I didn't label it, but this is the map C. If the image is infinite dimensional, then in this is an infinite dimensional C vector space. If it's infinite dimensional in that C vector space, then since this is a finite dimensional C of X vector space, we'll have a non-trivial linear dependence over C of X. Okay? And it's not too hard from that non-trivial linear dependence over C of X to cook up this first integral. Okay, but it's a technical construction. I don't think it's particularly enlightening, but this is the idea of the proof, which I think is pretty nice. Okay, so how does this relate to the things that Dave Marker and Rahim Moosa talked about yesterday? Well, so this is a slightly generalized version of the definitions of D varieties. Okay. So I'll call VS, this pair, a D variety of type R if for each A in V, SA is an R-dimensional affine subspace of the tangent bundle of V. Okay, so given by some linear relations in the tangent bundle. Okay, so that the space is dimensional. So, and a rational function f in C of V, I'll call it D constant, if it's true that for a general point, A and V, DFA vanishes on SA.
This is not the same definition of D variety that you guys.
As what?
As Rahim's definition.
No, I said this is a generalized version.
So when R equals 0.
When R equals 0, this is the same as Rahim's definition, because then SA is just a section. Okay, but let's suppose that we're given a D variety with no non-constant D constants, then what we basically proved via translated to this language, the Jouanolou style theorem, is that VS has only finitely finitely many codimension 1 D subvarieties. Okay? And all right. And if you work just a little bit harder, you can actually take away, you can actually also cover the case where R equals dimension minus 1. Okay? I don't want to, again, in the interest of time, let me skip those technicalities. But let me put this statement of the theorem on the board again and explain something why in the setting that Rahim described yesterday for D varieties, there was a functorial correspondence between the D subvarieties and the differential algebraic subvarieties of that corresponding differential algebraic variety. That's no longer true in this case. And it's obvious if you just work with a fixed example. Okay? So by definable sets, you can think differential algebraic subvarieties. Okay? So when you have a D variety like this, it's akin to having an underdetermined system of differential equations. It's like having fewer equations than the number of variables, essentially. That's a simple case in which this occurs. Now, if that happens, there's really no hope of having a functorial correspondence between the subvarieties of V itself and the differential algebraic varieties, because the problem is that those differential algebraic subvarieties could be defined by higher order differential polynomials. So you'll have to prolong V in order to get some functorial correspondence. And if you're interested in all of the differential subvarieties, there's no bound to how far you have to prolong. I mean, you know that affine one space is a generalized D variety sense, where I take S to be all of the prolongation. Well, there's no bound to the order of the equations that define differential subvarieties of that. I mean, that's silly. But the point is that when you're given a generalized D variety in this sense, if you insist that the subvariety you're interested in is co-order 1, then there is such a bound. Okay, so not in general for all subvarieties, but for those that are co-order 1, there is a bound. Okay. And I think there could be some easier proofs of this. I'm not sure particularly. Of course, in the ordinary case, this is very easy to prove. You can do it just in a very hands-on way. In the setting of partial differential equations, the proof that Rahim and I gave involves basically some bounds in certain uniformities, but in a certain way it relies on the kind of combinatorics that William Sitt used to show that the Colchin polynomials are well ordered. That's somehow the essential. We use characteristic sets, in short. Okay. But we use the theory of dimension sequences, which I'm not expecting anyone knows, but if you want to look in William's paper, you can see that. Okay. Okay, and we use that to prove the following theorem, which is somewhat more satisfying if you're really interested in differential algebraic varieties. So, following our equivalent. And here, recall that I equipped little k with the constant derivation. And so, as I mentioned before, when little k is not the constants, there's no reason for this to be true in general at all. And there are counterexamples which show that it is not. But we can do a little better. What we can prove is that when F is a finitely generated delta field extension of K, so I mean finitely generated as a differential field, then we can prove the same theorem. Okay. And well, sorry, go ahead.
Every delta variety defined first?
Yeah, it is. That's right. But But if you consider the co-order 1 subvarieties, they might not be, right? Okay. So, yeah, so we can only say something about the co-order 1 subvarieties that are defined over F. Okay. It is in this form. Okay. So you have no hope of proving this theorem for if you allow infinitely many differential generators.
Is there any relation between this and what Thiel presented last workshop?
I'm sorry, I just can't hear you.
You were here at the last workshop, right?
Yes.
And he gave a talk on parameterization for
Yeah.
solutions. So is there any relation?
Yes, definitely. If you pick a, so let me see if I can just recall what he said for other people. I think that you were considering an order 1 differential equation over C of t, which was it an arbitrary order 1 equation or rational? I can't remember.
Just order 1.
Just order 1 but arbitrary. And he was looking at when there's infinitely many rational solutions to that equation and trying to parameterize them and find a generic solution. So if it were the case that there were only finitely many C of t solutions to an order 1 equation, then there would be no map like this, and there would only be finitely many points like this. Okay, so for that situation, these correspond to the C of t solutions to the equation, because co-order 1, when you have Poisson polynomial 1, means a point. So yeah, it's, I mean a family defined as a family defined as a family of differential algebraic varieties. So you have each element in the family defined by an equation f of xa, but the a varies over possibly a parameter set, which again is a solution to a differential equation.
The word uniform could be redundant, I guess you could just call it a family.
I could just call that a family. Model theorists tend to call that uniform.
So let me see if I understand something. So one way to attempt to violate this theorem would be to have, say, or I guess one way to try to violate the equivalence between 1 and 2 is to try to have a family of order 1 subvarieties that are indexed by something that is orthogonal to the constants.
That's right, and that's exactly how you build a
That doesn't
constant.
happen.
Yeah, so if you, for instance, I think a lot of people are familiar with this, if you take one of the order 1 equations, say given by Rosenleet when he was proving the non-minimality of differential closure, and you take the field which is obtained over the rational numbers by adjoining infinitely many solutions to one of Rosenleet's equations, then of course, in that field there are infinitely many solutions to Rosenleet's equation. But there's definitely not a map to the constants because Rosenleet showed that there can't be any solution. But what this theorem says is that only such counterexamples arise from doing something like what I just described.
And sorry, and what you just described would arise because then the little plane would be wrong?
The field can be finally generated.
The field won't be finally generated because I just adjoined infinitely many solutions.
I see that, okay.
So, I mean, you almost previewed this, but order 1, what this proves in say some of the language of Dave Marker's talk yesterday is that order 1 strongly minimal sets are non-orthogonal to the constants. This was the goal that I believe that Udi had in mind when he worked through this the first time. I'm sorry. I'm sorry. Yeah, this is very confusing. Should say orthogonal. Yeah, that's a typo. It's the worst kind of typo, the one that makes you entirely wrong. I'm sorry, my fault. So, order 1 strongly minimal sets, which are orthogonal to the constants, are Aleph non-categorical. And okay, so if you're a model theorist, this is probably already obvious from what we said already, or at least you start to see how to prove this. But if that were not the case, what it means for an order 1 strongly minimal set to be non-categorical is that the algebraic closure relation on the set of solutions is infinite. It has, if you take the algebraic closure of some finite set of solutions, you can get infinitely many solutions. So for instance, this would happen if you had some kind of differential algebraic variety that defined a group, and you could multiply the solutions and get new elements in the group. As long as you didn't start with the torsion element, you would get a lot of solutions in that way. And what this says is that for order 1 equations, the only way that you have a process like that is when you have a map like this.
So, for example, this says that things like monotrials.
No, those are not order 1,
Exactly. That's
unless
what I
they're
was
defined
going
over the constants.
to say. That's what I was going to say.
Oh, okay, sorry.
And also the equations that, the example that you and Tom had of something coming from the J function being not categorical
Yeah.
is therefore also not an order 1 equation.
Right, it implies the equation that we proved to be not categorical is an order 3 equation. Although we specifically wrote down the equation at the start.
I'm just trying to organize thoughts in my head, I'm sorry.
Another corollary is the following theorem, and I think it was mentioned slightly by David Marker last time. I think in the interest of time, I will give you just a very, very brief sketch of the proof. I'll explain how to do it. To give you some idea of the history here, I don't know exactly when the question was asked, but at some point there was a question of whether U rank would be equal to Morley rank in differential fields. And that was answered negatively by Udi and Tom around 1998 or 1999. And their example has transcendence degree 5, or algebraic dimension 5 in the sense of Dave's talk yesterday. And they end their paper by saying, well, Dave and Anand have a proof for order 2 sets over the constants that Laskar rank equals Morley rank. And all the known examples where Laskar rank doesn't equal Morley rank have transcendence degree at least 5. So is there a theorem that explains that gap? And well, here's a theorem that explains part 1/4 of that gap or something like that. Okay. And I'll give you a sketch of the proof. If you have Morley rank 1, then you have Laskar rank 1 by generalities. So we don't need to consider that case. The other option is that you have Morley rank 2. If you have Morley rank 2, it has to be that you have infinitely many code order 1 subvarieties, because you have to have infinitely many transcendence degree 1 subvarieties, each of which don't intersect. Technically, we can arrange that. And once you have those, then you can get a map to the constants, and you can get a uniform family. And that gives it a transcendence degree 1 forking extension of your generic point, which witnesses that this set has U rank 2. Why is what I said right there a slight lie? Well, the slight lie is that when you calculate Morley rank, you don't get to do it over, it may be that the parameters you used to define those equations came from something bigger, some bigger field, but you can maybe that to define those equations, those Morley rank 1 sets, you had to look in K-alg, the field you started with. But that's okay. You do some sort of Galois theory type argument, and you can sort that out.
Which might have to do with differential equation.
Yeah, but you can sort that out.
Right. I mean, so even though it might be the case that you have to go to, so that you might take a final general extension, it gets more code for the 1 sets, more code for 1 sets.
Well, if our proof is right, then you could sort that out. Okay, I haven't given the details though, so. Okay, so I'd like to stop there.
Thank you. Are there any questions? Any other questions, I should say?
Yeah, so actually, I'm still a little skeptical about the theorem over F over final general extensions. So that would seem to imply that if you had a family of, say, order 1 differential varieties parameterized by finite dimensional differential variety, then it should be non-orthogonal to the constants, the generic constants. Well, I mean, if the given base variety property that's over different fractions, or the differential field of functions, and it points, like say, semantic kernel is orthogonal to the constants over its, over some final general field would have infinite points, and we did infinite fibers. That's family of order 1 differential varieties. That's where's the map? Where's the value?
But aren't you talking about the total space of the Manning kernel crossed with, basically, is your underlying variety the Manning kernel and then something above each point in the Manning kernel? That's what you're taking.
Yeah, I was thinking that one thing is the total space in the Manning kernel, and then something over that.
Yeah, but once you take each point in that Manning kernel, you're already at co-order 2. Because those are torsion points in an elliptic curve. So they're algebraic over the field of definition.
No, over it.
I'm not sure. I think that we might need to write things down for me to understand.
They're not different. It's like just like a generic point in Manning.
But yeah, I'm not sure I precisely understand.
Yeah.
Because I'm not sure I precisely understand. Sorry.
We can leave that perhaps for afterwards. Are there other questions?
Remember, Jouanolou theorem includes some bounds on the number of these.
Yeah, that's right.
Do you have any in your theorem?
In our work, we haven't computed the explicit bounds, but I think Rahim and I have talked about this only briefly. I believe that they're in principle you can calculate them in a similar way as what Jouanolou and then some later people calculated even more bounds. We haven't done that yet, but I would imagine. In principle, there's nothing preventing one from doing that. I'm not sure.
Okay. Other questions? Well, I thought just the earlier comment here is you figured that algebraic versus differential.
Yeah,
So the, well, thank you. That finishes the talk part.
So we're running about 15 minutes late, which is fine. So we're going to take a 15-minute break, and then the people who know they're supposed to meet in pairs will meet in pairs with their first pairs at 2:30. And if you don't know who you're supposed to talk to, come talk to me. And if you have no idea what I'm talking about, that means that you're not one of those people, and you can talk to whoever you want. And in any case, people are very welcome to hang around and chat, and talk about math and think about math, and eventually in a few hours there will be pizza for dinner as an incentive to hang around and do math. The coffee will also not remain available. Yes.